my experiences of teaching the mole concept to Year 11 to 12 students in the Northern Territory. To begin with, I start off with the idea of constructivism, and in order to do this, I need to first find out what the students know. So what I did first up is I asked their teacher last year. Secondly, I asked the students, are you confident? Do you know what you're doing? And they told me, yeah, miss, we're all over this. But luckily, I asked a third question. I asked a specific question. I said, what's a mole? And when they couldn't give me answers, I tried for a written test. I gave them a complex calculation and asked them to write anything they know. And what I found from my investigations is the kids didn't really know much, so we decided to start from the basics. Now, a lot of students struggle with the concept of moles, and I've noticed more often than not, my students, as soon as they don't understand something, they put up a wall and they go, Miss, not going to take anything in. So I started with making them as comfortable as possible by drawing their attention to specific concepts that they already knew really well and were important for our moving to a stronger conceptual model of the mole. So we started with a hands-on and minds-on approach. They were given 12 medals. They were all the same shape and size, about that shape and size, and I asked them two simple questions. I said, firstly, what do you notice? And 2, can you find any pattern between what you notice and their placement on the periodic table? The ensuing discussion led us to the conclusion that all elements or atoms have different weights, and the weights are based on the number of protons and neutrons. The more protons and neutrons, the heavier the atom is. And then I related that to mass number, and that was the first place that I connected the concepts with the calculations I knew they were going to be doing next. So the next lesson they walked in and we had a Socratic conversation with really great success to build on their current mental models. The questions I asked started simple, such as, are all atoms the same? And then required increasing amounts of thinking. We went from, is a pair of helium atoms the same weight as a pair of lead atoms? Which one's heavier? We went from pair to a dozen to a gross, all the way to 6.022 times 10 to the power of 23 lead atoms. Is that heavier than 6.022 times 10 to the power of 33 helium atoms? We then identified this number as what we call a mole, an Avogadro's number. I explained the significance of the mole and Avogadro's number, that it allows us to tell exactly how many atoms we have based on the weight of them. And then they began with basic calculations. I asked them to find the mass of 1 mole of helium, calcium, hydrogen, atoms they were familiar with. The next lesson they came into a lab-based experience. They had to measure tangible things they were confident and familiar with, like coins, pins and pencils, and they related the number of those items to the weight of those items. Over the double lesson, they were slowly put through many calculations, with 12 of them, a dozen, 4 of them with an arbitrary name, and then the mole. So you can see that they were slowly moving from the tangible, things they could touch, to intangible, invisible things, both conceptually and mathematically at the same time. The kids worked in groups, and I could see that they slowly developed really sound mental models of the mole concept. The next step was that I asked them to derive their own formula. I didn't want them to just memorize a formula. I wanted to get them to think about it from the very start. So I asked them in groups to derive a formula for number of moles when given mass and molar mass. Then I asked them to find different versions of that formula. It was a big discussion. It started off with I do, we do, you do, and eventually they were asked to establish their own mole relationship triangle. After this point, differentiation was necessary because I had one student with really low maths and science background, and she needed extra scaffolding to understand how to apply that equation, and I used different representations. I used a modelling kit to help her understand how that worked. At the same time, other students could work ahead. They were given heaps of practice questions that gradually got harder and harder. When they were confident with that concept, they had to derive their own concentration volume relationship using their own problem-solving skills, which they did really successfully. Now, I continued to push problem solving as we went through this and gave them extension questions that didn't really have a clear set way to solve. And this was really good for the kids because they're not really used to not just applying a formula that they haven't thought about. And I found this really helped the kids emphasise the relationship between maths and concepts and really got them to think. The next step was moving on to stoichiometric calculations, which I used modelling kits, the whiteboard and discussion again. And then we moved, once they were confident with their stoichiometric calculations, we moved back into the lab. So they calculated the amount of mass they needed for a certain concentration, then they weighed the mass, made up that concentration. They diluted it, they reacted it with something and used followed what they did in the lab with their maths to find their concentration of an unknown. That was a really good diagnostic assessment, and I saw that the kids were really good at relating concepts and maths and problem solving, putting it all together in a new context. Their final assessment of understanding was a titration assessment and test that included lab work, conceptual questions, and maths-based questions. Overall, it was really successful, with all students achieving higher marks in this topic than any other in chemistry so far, and all of them showed really significant growth. Thanks for listening.